Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 12th grade topic, function continuity. If you're new to my channel, I'll be putting time codes in for this video in the description box below. So use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what we see today or even on homework, you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist in which I cover a lot more topics. So if you're interested in that, make sure you stay tuned. This video is going to have 4 parts, so leave a like, smash subscribe, and let's get started. In today's video, we're going to be covering function continuity. More specifically, we're going to be covering 3 types of function discontinuity. However, before we get into what makes a function discontinuous, let's first talk about what makes a function continuous. A really watered down basic definition would be a function is continuous if it's defined for every x value in its domain. Now, I say that's really watered down because there are some discontinuous functions that still fit that bill. In order to get a more full and robust definition, we're going to need to talk about limits. However, we'll cover limits in another video. This is going to be 90% of the way there. Most of our discontinuous functions will contradict that statement. However, there are some that do fulfill that statement and are still discontinuous. Hence, this is a watered down definition. But like I said, most functions are defined at every x in their domain. They're going to be considered continuous. That means we have constants, we have linears, all your polynomials, higher degree polynomials, your quads, cubics, etc., all of those polynomials are going to be considered continuous functions because they exist at every x in their domain. And these are not all of them, there are a lot more, but these are going to be just an idea of what a continuous function is. So what makes a function discontinuous? Well, similar to how we had a dilemma when trying to make a definition for continuous functions, we're going to need to rely on limits. However, another watered down definition that'll get us 90% of the way there is going to be a function that has at least one x value that is not defined on its domain. Once again, there will be some discontinuous functions that will contradict that definition. It's a watered down definition, but it gets us at least 90% of the way there. Come back for my limits video where we get a more in-depth definition for a continuous function and a discontinuous function. So like I said earlier, there are going to be 3 types of discontinuous functions that we're going to be covering today. The first is going to be your whole discontinuity. The second is going to be your infinite discontinuity. And your third is going to be your jump discontinuity. All 3 of these are going to be discontinuous functions, however, they look very different. A generalized graph of your whole discontinuity will be something like this. Let's say we have this, and instead of being continuous everywhere, we have a nice hole. Hence, whole discontinuity. You should be very familiar with your infinite discontinuity. Let's say we have something like this. We have an asymptote and something like that. This is going to be an infinite discontinuity. You're going to infinity and negative infinity, and you're not really converging on the point. The last, our jump, is going to look something like this. Let's say we have a function here, and we have a hole here, and a function there. This is going to be an example of a jump discontinuity. Something else you should know about discontinuous functions is that there are some that are removable and some that are not removable. This jump is not removable. This infinite is not removable. However, this whole is removable. I'll talk about what makes them removable or not removable a little bit later in this video. Now that we've covered the 3 different types of discontinuous functions, let's dive into each one and cover what their function forms may look like. So when talking about your whole discontinuity, most of them are probably going to look just like this. Now, what makes this a whole discontinuity? Well, your whole discontinuity is going to be where your denominator equals 0. However, it can be removed. Now, how is this going to be removed? First, let's factor the top. So we have x plus 4 in the denominator. X squared minus 16 can be broken up into x minus 4 and x plus 4. Notice we have an x plus 4 on top and bottom, which means we can cancel that out, which leaves us with x minus 4. What does this mean? This means that x squared minus 16 over x plus 4 most of the time looks like x minus 4, except at where this denominator is going to equal 0. Now, where does this denominator equal 0? Well, x plus 4 equals 0 at x equals negative 4. So most of the time, this function looks just like this function. However, it's not existing at x equals negative 4 because your denominator can never be 0. This is what makes this function discontinuous, and the fact that we can cancel these out makes it a removable discontinuity. In fact, another property of your removable discontinuity is that you can technically make it a continuous function by simply filling in that hole. So what value do we need to fill in the hole with? Well, you just take this, plug in your missing x, and see what the value of the function would be if this was the actual function that we had. So let's plug in our x equals negative 4 into this right here and see what we get. This is going to be a negative 4 minus 4, which results in a value of negative 8. So this is going to be the value that it doesn't have, but if we want it to be a continuous function, we're going to plug it in. So I'm going to graph this. I'm not going to graph the rest of them, but for this one, it's a fairly easy one. So I'm going to graph this, and it's going to be looking a little something like this. So we have something like this where you have negative 4. It looks like x minus 4. At negative 4 here, we're going to have that hole there. And this is the typical graph of this function. However, if we want to make this into a continuous function, all we got to do is make this into a piecewise function. So instead of f of x, we'll have g of x equals, we're going to have f of x, whatever that f of x is, whenever x doesn't equal negative 4. And we're going to have 8, negative 8, when x does equal negative 4. So we're making a function continuous from this discontinuous function by plugging in the missing value. You can do this because it's a removable discontinuity. So you can cross out the thing that's in common, and if you want to make it continuous, simply plug in the missing value. For everything else, it's going to be this f of x. However, because it doesn't exist at x equals negative 4, we're going to have to plug it in, and by doing so, we fill in this hole. So this is the example of a hole discontinuity. Let's jump into our infinite discontinuity next. Let's say we had this function, f of x equals 1 over x. Now, this is probably going to be a very familiar function to you at this point in time, but you notice that this doesn't exist at x equals 0. But unlike our hole, our removable discontinuity, there's nothing to cross out here. Hence why this is not removable. You can't get rid of that. This is all we have, and it's going to be an infinite discontinuity because we have asymptotes involved now. Instead of a hole, there's an asymptote. So your infinites and your holes look pretty similar. They both are going to be discontinuous because the bottom doesn't exist at some value. However, your hole, you can remove it, whereas your infinite, you can't. Now you may find yourself in a situation where you have both a hole and an infinite discontinuity. But you're going to have to do the math and figure out how you got that. So let's say we have something like this. X minus 4 over x squared minus 16. Now we're going to factor it. You got to make sure you factor these out so you can really see if anything can be removed. By doing that, we're going to have x minus 4 on the top. X squared minus 16 is going to have x minus 4 and an x plus 4. And notice that x minus 4 exists top and bottom. That can be removed. So we're going to have just x plus 4 on the denominator where we have a 1 in the numerator, which means our function kind of looks like this, 1 over x plus 4. So where is our infinite discontinuity? Well, our infinite discontinuity is going to be where this goes to 0. So how do we make that 0? By plugging in x equals negative 4. X equals negative 4 is going to give us an infinite discontinuity. However, that's not the only one we had because we crossed out something here. So where does this go to 0? Well, this was an x minus 4. So x minus 4 means that x equals 4 is going to be a whole discontinuity. This is removable, and this is not removable. So you see, you can have multiple discontinuities in a single function. Just take your time, break it down, and factor where you can to see which ones you have, if not both of them. But now that we've covered infinite discontinuities, let's jump into our jump discontinuity. So our last discontinuity for today is going to be our jump discontinuity. And this is going to be the typical form of your jump discontinuity, a piecewise function. Now that doesn't mean that all piecewise functions are going to be discontinuous functions, but this is going to be the typical way that you'll see your jump discontinuities written. So what makes this a jump discontinuity? Well, a jump discontinuity is going to occur when you have a function that behaves like multiple functions, however, they don't connect at their intersection points. So if you look at this right here, we have a function, however, it behaves like two different functions. We have x plus 4 and we have negative 2x minus 11. We have two different functions here. And if we're going to graph both of these, you'll notice that they don't meet at their intersection point of negative 2. So if we were to plug in negative 2 to the top, you'll see that we're going to have negative 2 plus 4, which gives us a positive 2. If you plug in negative 2 to the bottom, you'll see you have negative 2 times negative 2 minus 11, which gives you a 4 minus 11, which gives you a negative 7. These do not equal. These do not equal. Therefore, there's going to be a discontinuous action happening where they're supposed to meet at negative 2, thus causing our jump. Remember, your jumps are going to look a little something like this. Something is coming from the left, something coming from the right. However, there is a jump here that does not meet. That's what's going to happen here. Positive 2, negative 7, they don't meet. And this is why not all piecewise functions are going to be jump discontinuous functions. Because all you got to do is have two functions, even if they're different functions, meet at their intersection point and you don't have a jump discontinuity. And you can also see why this is not removable. We can't just remove this discontinuity because it just behaves too differently. There's multiple functions not joining together. You don't even have to have just two. You can have more than two. You can have 3, 4, 5. It doesn't matter how many functions, as long as two of them do not join together at a particular point that they're supposed to meet, that's when you're going to have that jump discontinuity. Well, I hope you were able to follow along with today's video and hope you now understand your 3 different types of function discontinuities. However, if you have any questions about what we saw today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found this video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share the video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework. I'm looking forward to seeing you again next week. I'm Courtney. Here's your playlist, and it's been another session of Tutor Me Sempai.